This really will be the last mini lecture for Chapter 18. But, saving the best for last because it's all about synthesis. All right, so you know where we've been, you know where we're going. Synthesis is where it's at. I think I've said this enough times already. So what about synthesis? Well, as always, the key is to just look at what you're trying to make, the target molecule, and ask yourself, how can I make that in one step from whatever I want? Don't worry about anything else. Once you have figured out, this seems to me that I should be able to make this by disconnecting this bond or by using this chemistry, do it. Do the disconnection. Break your molecule, your target molecule, into pieces that consist of a reasonable electrophile, i.e. something you've seen before, and a reasonable nucleophile, something you've seen before. The good news is the aldol in particular gives you some pretty huge hints. So an alpha-beta unsaturated carbonyl is screaming, I've been made by an aldol reaction. So does a molecule that has a 1,3 relationship between a carbonyl and hydroxyl. So, for example, if I see this target, I'm going to say, ay, 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 aldol city, man, because I know that conjugated double bond very easily can form from an E1CB mechanism where I lose water across that 2,3 carbon, and when I look at that 1,3 relationship here, I know that if I push my lone pair back in here and push that pair of electrons back into that carbon, quite clearly I have an enolate that can add to an electrophile. So, looking at it from the forward direction, what we're talking about here is these two react to make an aldol that has not dehydrated. Further dehydration, loss of water, takes me to the conjugated ketone or aldehyde. So, what am I saying? I am saying when you see a target with that functionality, alpha-beta unsaturation, or this functionality, 1,3 carbonyl hydroxyl group, you're going to use an aldol to make it. All right, there's another screaming bell and whistle in synthesis for the Michael reaction, and that's the 1,5-dicarbonyl. So whenever you see a target that says 1, 2, 3, 4, 5, I have carbonyls 5 away from one another. Boy, oh boy, that's telling you I am going to add an enolate right here to an electrophile right there. What's my electrophile? My alpha-beta unsaturated carbonyl. That's interesting. So that probably was made by an aldol, but that's just an aside. So, looking at it forward, we're talking about making this enolate, adding it to the Michael acceptor. That gets me to, I'm not even going to try to draw the nice, I think that's a 8-membered ring? I don't know. 7-membered ring? I can't tell. So here is my intermediate, and as we know, that's going to collapse and get protonated by alcohol or something to give us our product. So 1,5 dicarbonyl, you're going to make a Michael. Here is a good question for you. Looking at this target, can you think of a different Michael disconnection that gives the same product? And you should be able to come up with one, because every Michael product, every 1,5-dicarbonyl, should be able to be made by two different Michael disconnections. All right, and last but not least, the Robinson annulation retrosynthesis. How's about doing one of those? Well, remember that the Robinson annulation pulls it all together. It's a Michael and an aldol. So when you look at this target, you see, that's aldol. So I should be thinking about how this guy came from the loss of water by some kind of so on. That looks like the aldol precursor to me, okay? Because I've got the 1,3 relationship between the hydroxyl group and the carbonyl. And sure enough, that makes sense. There's my aldol precursor. Well, how did I get there? Well, that means I added this enolate right here to a carbonyl right there, right? So that should look like this. Does this give me this? Absolutely. All is well. Okay. One step backwards, one step at a time. What next? Ah, when I see that, what do I have? A 1,5 relationship between my two carbonyls. There's my Michael step. So my Michael step is going to be either addition of an enolate right here to an alpha beta unsaturated carbonyl right here, or it could be that I'm adding an enolate here to an alpha beta unsaturated carbonyl there. And I have chosen to show you that one where I break off my Michael addition into two pieces, two separate pieces. So this is an intermolecular reaction where I'm going to add here and kick out my electrons onto the oxygen there. That should give me this guy. And of course, I'm skipping a few steps like the formation of that other enolate. This is just the brainstorming part, not the nitty-gritty details. And then, of course, where do these pieces come from? Where does this come from? And where does this come from? Well, obviously the enolate for that ketone comes from the ketone. And the other piece, well, it's just that's your starting material. But you know, it's sure worth looking at the fact that that's an alpha beta unsaturated carbonyl. So I could make this by an aldol. So you might want to think about that. You can just keep going backwards even more. Or how about a Diels-Alder? That would be a good choice too. So you can just keep having so much fun with synthesis, like a kid in a candy shop. All right, that wraps up chapter 18. Lots to play with. Now, a bad joke. So if anybody in my class is from North Dakota, I apologize in advance. A couple of North Dakotans walk into a bar. They were so happy. They were celebrating. Give me a pitcher of beer. Bartender says, well, why are you guys so happy? He says, we just finished a jigsaw puzzle. It only took us 2 weeks. And the bartender's like, 2 weeks? Shouldn't take you that long to finish a jigsaw puzzle? And the North Dakotan said, are you kidding? The box said 2 to 4 years. Yeah, okay, whatever. Like I said, I apologize. And in the meantime, have fun with synthesis and aldols. We'll play a lot with these.